In this section, we are looking at the t-distribution. And this is the distribution of a random variable x that is approximately normal. And it has a lot of properties. So the mean, median, and mode are all equal to 0. The t-distribution is bell-shaped and symmetric about the mean. The total area under the curve is equal to 1. The tails of a t-distribution are thicker than those of the standard normal distribution. The standard deviation varies with sample size, but is always greater than 1. And the t-distribution is actually a family of curves, or you can think of it as a group of curves, where what's called the degrees of freedom determine the shape of the curve. And the degrees of freedom are equal to 1 less than the sample size. And as the sample size and degrees of freedom increase, the t-distribution approaches the standard normal distribution. And we can see that in this diagram here. We can use the t-distribution to help construct confidence intervals for the mean when the population standard deviation is unknown. The level of confidence C is the probability that the interval estimate contains the population parameter. For the critical values, the level of confidence probability corresponds to the area under the t-distribution between two t-scores. So in the last section, it was under the standard normal distribution between two z-scores. So these two t-values, negative tc and positive tc, are called critical values. Again, in the last section, it was negative zc and positive zc that were the critical values. Our degrees of freedom are n minus 1, so the sample size minus 1. The margin of error, E, is the greatest possible distance between the point estimate and the value of the parameter it is estimating, given a level of confidence C. So E is equal to Tc times S divided by the square root of n. So S is the sample standard deviation, Tc is the critical value, and n is the sample size. And this formula can be used when the following conditions are met. Sigma is unknown, but we know S. The sample is random, and then at least one of the following is true. The population is normally distributed, or the sample size is greater than or equal to 30. So this is very similar to the margin of error formula in the previous section. And how we construct the confidence interval is also very similar. To find the critical values Tc, we need to look at this table. And this goes up to 10 degrees of freedom. So depending on the level of confidence and the degrees of freedom, we can locate our critical value. A random sample of 5 people is chosen. The sample mean driving distance to work was 22.2 miles, and the sample standard deviation was 5.8 miles. Assume the driving distances are normally distributed. Construct a 95% confidence interval for the population mean driving distance. Interpret the results and show all work. So our sample size is only 5. However, the population is normally distributed, so we're okay. The degrees of freedom are equal to the sample size minus 1. So 5 minus 1 is 4. X bar is 22.2. Now we don't know sigma, but we do know the sample standard deviation. So we do know S. It's 5.8. And then lastly, we need to find the critical value T95. So we need to look this up on the table. So on the table, we are in the 95 column, and the degree of freedom is 4. So our critical value is 2.776. So that is our critical value. So the margin of error is equal to 2.776 times 5.8 divided by the square root of 5, which is equal to 7.20. So now we can construct the confidence interval. Mu is between 22.2 minus 7.2 and 22.2 plus 7.2. So the mean is in between 15.0 and 29.4. So with 95% confidence, we can say that the true population mean driving distance is between 15.0 and 29.4 miles.